Okay, so in the previous one, we just changed the right hand side of only one variable. That was for the machine 1. Today, what we are going to do is, we are going to change it for the second one only, and we see how much change we get in the objective value, and see which machine is more preferable to change the maximum time of it, the shift time of which machine is more profitable or more preferable to change. And I just introduce the sensitivity, that it is the examination or it is the interpretation of how much change we are going to get in the objective function if we change the right hand side of the constraints or the coefficients of the objective function. And it is done in two main methods. The first one is the graphical one, and the other is algebraic one. Algebraic can also be termed as the simplex one. So yesterday, what we did was that we changed the time of the machine from 8 hours, machine 1 from 8 hours to 9 hours. And then we plotted the original one and the changed one in a single graph, this one. And we saw that if we change the machine 1 time from 8 hours to 9 hours, what we get is that the original, we get $128 of profit per day. But if we change it from 8 to 9 hours, what we get is we get $142, which means that we get $14 more than the original one. It means that changing the time of machine 1 from 8 hours to 9 hours is profitable by $14. So if we change it for like 3 hours, what we get is we get $42 extra. And the total is $170 instead of $128 that we used 8 hours and got originally. Now, what I will do is, I will change the time for the next constraint, the machine 2. And we see, what we will see is that we will compare that which machine yields more profit by changing its time from 8 to 9 hours. In exam, you may be asked like, okay, this one is the dual or shadow price for the machine 1, and this is the shadow price for machine 2. Which machine is more profitable to change the shift time of it from 8 hours to 9 hours, or from 8 hours to 10 hours? And you will answer that by doing this process. Okay, so now I will change the machine time of the machine 2 from 8 hours to 9 hours, and we'll see that how much change we get in the objective value. Now, we will also do it using the single graph, plotting the original versus the changed constraint. Now, we will dissect the page into original and change right hand side for machine 2, and we change it from 8 hours to 9 hours. Now the original is maximum z is equal to 30x1 plus 20x2 subject to 2x1 plus x2 less than or equal to 8, and the second constraint is x1 plus 3x2 less than or equal to 8. While in the changed one, what we use is the objective function will remain the same, which is 30x1 plus 20x2 subject to the first constraint will also remain same, because this is machine 1. By m/c I mean that it is machine, okay? And the second one will change, x1 plus 3x2 s less than or equal to 9. Here we use 8 and here we use 9, and this is machine 2. Now, just like we do in algebraic in the graphical method, we will plot both of these scenarios into a single graph, and we will see how much change in the profit we get by changing the time of machine 2 from 8 hours to 9 hours. And then we will compare both the machines, and we will answer that which machine is more profitable. So here we will do like x1 for constraint 1. For constraint 1, 2x1 plus x2 is equal to 8. First of all, we will equate it to the right hand side. We will remove this less than or equal to sign. Then we will put x1 is equal to 0, and we will find out that what is x2. So if we put x1 is equal to 0 over here, it will become 2 into 0 is equal to 0. So x2 will be equal to 8. And the second one, if x2 is equal to 0, then if we put x2 is equal to 0 over here, what we get is 2x1 is equal to 8. It means that x1 is equal to 8 by 2 is equal to 4. Now, for second constraint now, we see that x1 plus 3x2, we will equate it to the right hand side, okay? Now we put x1 is equal to 0, so we get x2 is equal to 8 by 3. Now, if x2 is equal to 0, what we get is, we will get 3 into 0 is equal to 0, so x1 is equal to 8. Now, we will plot this one, but before doing it, we will repeat same procedure for the changed right hand side for the machine 2. Here, for constraint 1, what we do is 2x1 plus x1 is equal to 8. So if x1 is equal to 0 over here, x2 is equal to 8. And if x2 is equal to 0, x1 is equal to 8 by 2 is equal to 4. Here and here, because constraint 1 is not changed, so we will get the same results in both of the original and the changed one. But for the constraint 2, we will get different results because constraint 2 is changed. So x1 plus 3x2 is equal to 9. Implies that if x1 is equal to 0, x2 is equal to 9 by 3 is equal to 3. And if x2 is equal to 0, x1 is equal to 9. Now we will plot both these scenarios on the same graph one by one. First we plot the original one. As we know from the previous experience, this is x1 and this is x2. Now we will graduate it properly, like here it will be 2, 4, 6, 8, 10 and 12. Here it will be 2, 4, 6, 8, 10 and 12. Okay, so now the first point that we need to plot is 0 and 8 and 0 and 4. So for x1 is equal to 0, x1 is equal to 0, it means that this point. x2 is equal to 8, this is the next point. And for x2 is equal to 0, x1 is equal to 4. So we will join these 2 points. And the second constraint, for x1 is equal to 0, x2 is equal to 8 by 3, and it will give us 2.67, I guess. Let me calculate it using calculator. 8 divided by 3, yes, 2.67. Okay, and x2 is equal to 0, x1 is equal to 8. So first point is x1. If x1 is equal to 0, x2 is equal to 2.67. So 2.67 comes like this is 3, and this is like something 2.67. So the first point will be over here, and the second point is for x2 is equal to 0, x1 is equal to 8. So we will join both these points, and this is the optimal original, optimal O, or you can say that original. And here it will be somewhat something like x1 will be 3.8 or something, and x2 will be about 1.67 or something like that, or 1.7, and it will be like 3 point maybe 7 or 3.67, something like that. Okay, now we plot the second one also, okay, in the same graph. So we know that the first constraint is the same. The first constraint, this 8 and 4, this will remain the same. We need to plot only the second constraint. So constraint 2 is 0 and 3 and 0 and 9. So x1 is equal to 0, x2 is equal to 3, which is this point. And for x2 is equal to 0, x1 is equal to 9, which is this point. Okay, so we will actually joining these 2 points, and now the answer, the optimal point, is shifted from here to here. It means that it increases the, this is the optimal C or changed. Okay, so for example here, the for optimal O, x1 and x2, x1 is 3.7 and x2 is 2 point sorry 1.1.67, and for optimal C or changed, this is 3 and it is 2.2 or something. So x1 is equal to 3 and this is equal to 2.2 or something. Now we see that how much change. For this one, the z value is we know that it is 128. Okay, because we already did it for the previous one, and we were getting for optimal O 3.2 and 1.6. This is 3.2 and 1.6, where we were getting 128. And for the optimal C, what we are getting is z is equal to 30 into x1. So how much change are we getting? The graph is not that graduated because I did it, I approximated it. So I don't know if I get some. So it is giving us $134. So how much change are we getting? Now we need to calculate it. So change in profit by change in right hand side of machine 1 is equal to change in profit is equal to 134 minus 128, and here we get is 9 minus 8. So the total change is $6. So $6 per hour change. This is the change in profit or objective value. Now, we saw that by changing the machine one time from 8 hours to 9 hours, we get $14 more profit. But changing the machine two time from 8 to 9 hours, we get only $6 of more profit. So which one is more profitable to change?
The $18.
Machine 1, because changing the time of machine 1 from 8 to 9 hours actually yield $8 more than changing the time of the machine 2 from 8 to 9 hours. So machine 1 changing the time, the decision will be changing time of machine 1 is more profitable. This is the verdict. This is the decision. So that is how we do the sensitivity analysis. And we make decisions based upon sensitivity analysis. Now you see what is the benefit of it?
Yes.
Okay. So this was the first case of the sensitivity analysis, like changing the right hand side of the constraint. Now we will move to the changing the coefficients of objective function and see what are the changes in the objective value. So for this, we will use the same problem.
Same problem. Sensitivity. Problem. Big N. Problem A.
Do you hear me?
Yes.
Because your microphone is off. Okay. So here we can denote it as like maximize z is equal to c1 x1 plus c2 and x2, or minimize z is equal to c1 x1 plus c2 x2. Now c1 and c2, these represent coefficients of objective function. For example, profit per unit of product 1 is implied by C1. Similarly, profit per unit of product 2 is C2. So here, now we will change these C1 and C2s, and we will find out how much change do we get in the objective value. Okay?
Yes.
Yes, we know that the slope is equal to C1 by C2. This is the slope of this objective function. Okay. Now here, in order to be remaining in the optimal region, this is somewhat, this is the objective function line. This is actually the objective function line. And to be remain in the optimal or feasible region, it must be in between the both the constraints, the constraint 1 and the constraint 2. Okay. So now we will find out that how much change we can actually do in the objective coefficients.
So
The
this
answer
times
is
the slope.
optimal and it does not change. So for this, yes, minus C1 by C2, it is a negative slope.
Okay.
It can also be termed as C1 by C2, but this is the negative slope. Both are okay, you just have to, focus on the C1 by C2 value. The sign doesn't matter. Okay. So what we need to find is, we need to find this ratio C1 by C2 in order for each constraint to find range of optimality. Now, in this question that we just solved, we have maximize z is equal to 30x1 plus 20x2, and it is subject to two constraints. The first one is 2x1 plus x2 is less than or equal to 8, and x1 plus 3x2 is less than or equal to 8. Now, for this one constraint, this is C1 and this is C2, because it has 1 over here, but we do not write it. It also has 1 over here, but we do not write. This is C1 and 3 is C2. So for this, we have C1 by C2 is equal to 2 by 1. And for this, C1 by C2 is equal to 1 by 3. It means that we can change the objective coefficients in between 1 over 3 and 2. This is the maximum change that is possible, and the answer will remain optimal. This is the range of it. I will do it using an example. I will pick some value for C1 and C2 to change, and then we will see that if it's remain in the same zone, it will be optimal. If it does not remain in the same zone, then it will not be optimal. It will yield an infeasible solution. So here, for example, we will do an example over here. Example is that we change the coefficient of x1 or product 1 from 30 to 35, and we change coefficient of x2 or product 2 from 20 to 25. So we have the original one as 30x1 plus 20x2. This is the original one. Now the changed will be maximize z is equal to 35x1 plus 25x2. This is the new one. You understand it? We just
Yes. You
changed
have reference
the
for
value, this one C1 and this is C2. We change C1 from 30 to 35. I didn't, understand what you said.
Oh, I'm sorry. Do you have like a reference page number or the for this question?
Yes, 128. It is page number 128.
And 128. What's the question number like?
Chapter 3, it is 3.6-2.
Okay, thank you.
This is the reference number. This is the reference. Okay. So here, this is the new C1, C1 star. This is the C2 star. We know that this is the optimality region. Now here, we see that C1 star divided by C2 star is equal to 35 divided by 25. It yields 1.4. Now we see that 1.4, it lies between these two. So it lies between 0.33 and 2. So it will yield feasible solution, and solution will be optimal. And the new optimal solution will be Z is equal to 35 into 3.2. For x1 we got 3.2. For x2 we got 1.6 value. It can come from here. This one. The original x1 is equal to 3.2 and the x2 is 1.6. So I will just put the 3.2 and 1.6 over here, and the solution is $152. So simultaneously changing the coefficient by 5, we get $152. Now what we are doing is we will fix one and we will see that how much change we can bring in the second one so that the answer is optimal. And similarly, keeping the second constant and making changes in the first one to see how much change we can bring in that. So for this, we need to change This is question 2. Change in first coefficient C1 and C2 is it will remain same. So we have 1 over 3 is equal to less than or equal to C1 by C2 and less than or equal to 2. This is the optimality region of it. So if the 2 remain constant like 20, what we get is we multiply it. C2 moves over here and C2 moves over here. C1 less than or equal to 2 into 20 implies that 20 by 3 less than or equal to C1 less than or equal to 40. Now 20 by 3, this is equal to 6.7 or something like that. So 6.67 is equal to C1. Now this is the optimality region for C1. The coefficient 1, it can be increased between 6.67 and 40. If it is between 6.67 and 40, it will yield an optimal result. If we change C1 from 30 to like 5, the answer will be infeasible. And if we change it from 30 to 41, it will also yield infeasible solution. Between 40 and 6.67, it is yielding a feasible optimal solution. Similarly, if we can fix C1 and change C2, implies that 1 over 3 C1 by C2 is less than or equal to 2. So now here you can invert it actually, and 1 over 3 divided by C1 less than or equal to C2 less than or equal to 2 divided by C1. Now C1 is actually 30. So 1 over 3 by 30 less than or equal to C2 less than or equal to 2 by 30. So it will be equal to 30 divided by 3 is 10, and the other value is 2 by 30 is 1 over 15. So it will be somewhat 1 over 15 C2 less than or equal to 10. So this is the next optimality region for the C2. Similarly, like we got it for the C1. Okay, I will end this session over here so that we do not get any delay in the meeting.
Okay.
Okay? Yeah, if I do not end it and it ends by itself, then it will have like a delay of 10 minutes.
Okay.
It's already like 42 minutes and 20 seconds. Okay. C2, changing and get the C1 fixed. The C1 is actually 30 in here. And here it is C1 by C2. So the trick was to get the C2 in the upper position numerator and get the C1 down here in the denominator. So it will shift over here and this one will shift over
opposite.
over here. 1 over 3. So when it gets here, it will be get 3 over here. So now C1 is equal to 30. So we put this 30 value in here. So now the 30 is in the denominator, so it will get multiplied over here and also get multiplied on the both sides over here too. So 30 by 2 is less than or equal to C2 and is less than or equal to 30 into 3. So it will be like 15, C2 and 90. So this C2 actually the coefficient was maximum Z. We know that C1 x1 plus C2 x2. Now this C1 value actually it must be in between 6.67 and 40. And this C2 it must be in between 15 and 90. So this is how the sensitivity of the objective coefficients is determined. We just need to find the limits of it, with how much change that we can bring in the coefficient so that the answer remains optimal and it is not going to be infeasible or inoptimal. Do you understand it now?
Yes.
Okay. You must, practice it, before going to exam because this thing is a must, in this exam. Your teacher will must bring a question.
It's okay if you write more, like, just refer to more questions, just write more questions and I will solve it. I will practice for myself. Just the page number and the question number.
Okay, I will write it.
Okay.
Okay, after the lecture, inshallah, I will, write some questions to you and I can send it to you too. I will do it for the mathematical models too, and I will do it for sensitivity and the other things too. Because this sensitivity is a kind of very important thing. It is not that hard, but you need to just understand the logic of it actually.
Okay.
Once you understand the logic, then it is kind of very easy to, to pick any question and you solve it and get the solution. So now we will move towards the algebraic sensitivity analysis. This was all, the graphical one. Now we will move towards the algebraic sensitivity analysis. And in algebraic, we will also deal with two of the conditions. The first one is changes in the right hand side, and the other one is changes in the objective coefficients. So first, we will deal with the changes in the right hand sides of constants. So what the algebraic sensitivity analysis actually do is it determines the dual prices of a resource. Okay? And the dual prices actually
change in rate of right hand side of constant. Okay.
Yes, the dual prices actually is also called the shadow prices, and it represents the change in the objective function with respect to the change in the right hand side of the constants.
Okay.
Like we may increase or decrease the right hand side of the equation, the constant equation, by 1 or 2 or by 3, by any number, and we can solve it for how much change we are going to see in the objective function according to the change in the right hand side. So this change per unit, the per unit change, is called the dual prices or the shadow prices. So what the algebraic sensitivity analysis do, it finds out the dual prices for all the constraints. So here we have like a Tycho model, and it is a toy company which produces 3 kinds of toys, and we will solve it for that company, that how much change we can bring in the objective function while changing the right hand side by only 1 unit for all the 3 constants. Okay, so here we have the example, and the example is 3.6-3, also called the Tycho model. So actually what it says is Tycho uses 3 operations to assemble. The number of operations to assemble is 3, and there are 3 types of products, which are toy trains, toy trucks, and toy cars. So the daily available time for the 3 operations are 430 minutes, 460, and 420 minutes. So it means that the operations are the resources, and the
What is the
resource
base
1,
number?
the operation 1, has the page number is 128.
Okay.
Last paragraph. This is a kind of question that you need to also practice in order to change the descriptive form into a mathematical model. You can have you go at it, and you can see yourself like how much you can actually do. But let me simplify it for you. The other one is operation 2. I will represent operation 2 by OP2, okay? And the operation 3 with OP3, and the resources are minutes for operation 2 are 460, and for the operation 3 we have 420 minutes. So these are the 3 resources that will be used to produce these toy trucks, trains, and cars. Let's x1, it represents the trains, and x2 represents trucks, x3 represents cars. Okay, now it says that the revenue per toy train, truck, and car are $3, $2, and $5 respectively. So this one yields a revenue of, for x1 is equal to $3 per unit, and the revenue for x2 is $2 per unit. Revenue for x3 or cars is equal to $5 per unit. So these are the revenues which are given. So now when we mention revenues or profits, what comes in your mind about the mathematical model?
Maximize function.
Yes, this is a maximization problem. Yes. And we need, and these 3, 2, and 5 are the coefficients of the x1, x2, and x3 respectively. These are the coefficients in the objective function. So the objective function will be first, we know that it is a maximization problem, and then we know that the trains generate a revenue of $3 per unit, and the trucks generate a revenue of $2 per unit, and the cars generate $5 per unit. So this is the objective function. That is how you come up with the objective function. Okay.
Okay.
Then it says that the assembly time. Okay, we have 3 operations over here, like OP1 over here, OP2 over here, and OP3 over here. Okay, X1, it says that the assembly time per train at the 3 operations are 1, 3, and 1 minute. Okay, so the first one, actually, the train at operation 1, it takes 1 minute. Okay, in operation 2, it takes 3 minutes, and in operation 3, it takes 1 minute. Okay, I will multiply it with the x1 and 1x1. Okay, now coming to the operation, the second product, it says the corresponding time per truck. Actually, it is written wrong. It is again written train, but it is and per car are 204 and 120. So 204 means that the trucks are also operated in the first operation, and 0 minutes means that the trucks are not operated in operation 2, so it will get a 0x2, and 4 minutes for operation 3. Now the third, it says that the cars are 1, 2, and 0. It means that 1x3. The cars actually take 1 minute at operation 1, 2 minutes at operation 2, and 0 minutes at operation 3. And it must be less than or equal to the first minutes that we have is 430. Here in operation 2 we have like 460 minutes, and here we have like 420 minutes. So that is how you come up with the constraints of it. You see?
Yes.
Okay. So you must, read out the description, with kind of, attention, and then you will come up with the objective function and the constraints of it. Now, what happens if we change these right hand sides by some units? Okay, so let's change in OP1 time is represented by D1, and change in OP2 time is represented by D2, and change in operation 3 time is equal to D3. So now, when we change this time by D1, D2, and D3, we will get a new equation. the new equation will be x1 plus 2x2 plus x3 is less than or equal to 430 plus d1, while d1 represents the change in this time. Okay, now the 3x1 plus 0x2, or you can ignore it, you should not even write it, is less than or equal to 460 plus d2. We will write d2 over here, the d1 in the first constraint, and the d3 in the third constraint. You can ignore the x3, or you can write the x3 over here, and you can make the coefficient equal to 0. Now these are the updated constants according to the change in their time for each operation. Now this is a kind of 3 variable problem. Okay, and the table that we make using simplex will be as follows. I must make the table for it. We see that this is less than or equal to, this is also less than or equal to, and this is also less than or equal to. So I must write the 3 variables and
3 slacks.
3 slack variables. Yeah, 3 slacks. Okay, and then other side we have right hand side. Over here we will have z and s1, s2, and s3 over here. And here we will have -3, -2, -5, 0, 0, 0, and the right hand side will be also 0. The first constant we have x1 is equal to 1, x2 is equal to 2, x3 is equal to 1, s1 is 1, s2 is 0, and s3 is 0. Here s1 will be 0, s2 will be 1, and s3 will be 0. Here s1 will be 0, s2 will be 0, and s3 will be 1. And here for s2 we will have 3, 0x2 plus 2x3. And here we will have 1, 4, and 0. And the right hand side for the first constant is 430, 460, and 420. So this is the basic W that we can make. Okay, then it is a whole simplex problem that we need to solve, but we will jump to the final W of it, and from there I will show you a trick, how to find these d1, d2, and d3s for all the 3 constants, and we can find out how much change in per unit d1 can change the value of the objective function, how much change per unit change in the d1, d2 can change the objective value, how much per unit change in d3 can change the objective function. So I will find it out for all these 3 in the final table. Now if this one can be same, it can be written over here, and we can add this one, this d1, d2, and d3 also, then what will happen? Okay, so this is the right hand side. Okay, here we can write d1, d2, and d3, and correspondingly we can add, like here d1 is 1 plus 0 d2, we can write it as 0 d3. We can write it in this condition, in this form. Can we?
Yes.
Yes, sir?
Yes.
Yes, we can write it because here the coefficient of d2 is 0, so it means that it is 0. It is nothing. And here the coefficient of d3 is 0, so it means that it is also nothing. Only the coefficient of d1 is here, which is 1. So here we can write as in z all of these 3 will be 0. Because in the z we don't have any of the changes. We are only changing in the constants. Okay? So we will put the coefficients of d1, d2, d3 in the z row as 0, 0, 0. In the s1 row or in the first constraint, we see that only d1 is 1. So here we will put d1 as 1. In the s2, we know that only d2 is 1. And in the s3, we know that only d3 is 1. And the rest we can put as zeros and zeros. So this is the updated form of this W. Okay?
Okay.
But you don't need to solve it, in addition to it. You just solve it. You just solve it up to this, the right hand side. Okay?
Okay.
And in the question that will be given in the exam paper, you will be given the final iteration of it. You will not be given like you need to solve it like step by step and then do all the operations. You will be given a final table of it. So you can find out the answer of the z, x1, x2 and x3 if there is. Okay? So now I will write the final table of it. Now we see that. Okay. Here, if we focus. I am kind of making it boxes just to be it highlighted. Now see this highlighted region. What we see over here is 0, 0, 0, and here for d1, d2, d3 0, 0, 0. Here 1, 0, 0, and here it is also 1, 0 and 0. Here 0, 1, 0, and here is also 0, 1, 0. Here 0, 0, 1, and here is also 0, 0 and 1. Now what does it tell us? It tells us that whatever the value we get over here in the final table, it will also be the value for the d1, d2 and d3 in the final table. Final iteration. Whatever the value of s1, s2 and s3 is in this row, we are also getting d1, d2 and d3 of the same value in the same row. So that is why you do not need to solve it for d1 and d2 and d3. You just solve it up to this portion, and then we can replicate actually the values of s1, s2 and s3 into d1, d2 and d3. You understand it?
Yes.
Hello?
Yes, I do understand.
Okay. So now we will move to the final iteration. I can solve it actually. I can solve it, but it will take me like 20-25 minutes to solve it, because it is 3 variable problem, and we will have like 5 or 6 iterations of it.
We can put it in the PC in the Torah.
Yes, we can do it using Torah. Should I do it on Torah?
Yes.
Okay. Let me do it on Torah. I will show it to you. over here. So here I will open Torah. I will write Tycho over here as the company name, and the number of variables are 3, and the number of constraints are also 3, and I will put enter. Now the first variable name is frames. The second one is trucks, and the third one is cars. Now it is a maximization function, so I don't have to change it. It is already maximization. So here I will put 1 to 1, 1 to 1, and it is sorry, it's a maximization function, and 3 to 5, it is 3, 2, and 5, and here it is 1 to 1, and it is less than or equal to 430 minutes. The second constraint is 302. 0 is already there, so we don't have to change it. Less than or equal to 460. And the third one is 1, 4, and 0. 1, 4, and 0, 0, we don't need to write it, and it is equal to 420 minutes. Now we need to solve it. Go to the solve menu. You don't need to save the data. We solve problem by algebraic method, and we use the iteration method. What method should I use? I should all select starting solution and go to output screen. Okay, so this is the first iteration. Okay, we go to the next iteration. We see that car with -5 is the first entering variable, and x5, which is S2 in our question. Okay, this is the outgoing variable. We go to the next iteration. So in iteration 3, we get the optimal solution of it, and I can write the optimal solution from here into my page. Okay, so now we put this is the basic variable. Here we have z. Here we have x1, x2, x3, s1, s2, and s3. And here we have solution on right hand side. You can say any. And here in the final we have x2, x3 over here, and s3 over here. Here we don't have x1 over here. Okay. Now it is 4, 0, 0, 1, 2, 0, 1, 2, 0, and the solution is $1350. Okay, for x2 we have is minus 0.25, 1, 0, 0.5, minus 0.25, 0, and 100. The x3 column, x3 row, we have 1.5, 0, 1, 0, 0.5, 0, and 230. For the S3, over here we have 200 minus 2, 0, minus 2, 1, and it is 20 in the solution. Okay. So now this is the final table of it. Now we must write D1, D2 and D3 over here. Now S1 over here is 1, so D1 will always be, it will also be 1. S2 over here is 2, so D2 will be 2. And S3 is 0, so D3 is also 0. Now for this one, we have S1 is equal to 0.5, so D1 will also be 0.5. S2 is minus 0.25, so it will also be 0.25. And S3 over here is 0, so D3 will also be equal to 0. Now in this one, we have 0, 0.5 and 0. And here we have minus 2, 1 and 1. So you understood it how I replicated the values of S1, S2, S3 into the D1 and D2 and D3 column?
Yes.
Yes. So you don't need to solve it for D1, D2 and D3. So whatever the values are for here for the in S1 column, S2 column and S3 column, you just copy these 3 columns into D1, D2 and D3. You don't have to do some other calculations for it. Now I will now here from this section solution onwards, we are going to make the equation for Z, X2, X3 and S3. Okay? So first starting from the Z row. So Z over here, it will be equal to 1350 plus 1D1 plus 2D2 or 0D 3. You can add it or you can just ignore it. Because it will yield 0, so it is not significant over here. Okay? Now for the X2, we have 100 plus 0.5 into D1 minus 0.25 into D2. So here X1 is equal to 100 plus 0.5 D1 minus 0.25 D2. So for X2, sorry, for X it was for X2. So for X3, because X1 is not present here. It means that what it means if X1 is not present here. Yusuf?
Yes.
X1 is not in this column. So what does it mean? X1 is not in the basic variables.
It's a leaving value or?
No, it is 0 actually.
Okay.
Any basic variable that is not present here, it means that is 0. It means that the trains produced are 0. Yes. So we have Z, X2, X3 and a slack variable S3 over here. Now we will make the equation for 5D2 and 0D3. So we can substitute it as 230 plus 0.5 into D2 because D1 is 0 and D3 is also 0 over here. And S3 is equal to 20 minus 2 into D1 plus 1D2 plus 1 G3. Okay. So these are the equations that we found. Now just take the z over here, and it is 1350 plus 1d1 plus 2d2. Now what does it mean? The answer lies in this. The sensitivity answer lies in this equation, the updated equation. It means that changing the time of operation 1 by 1 minute or 1 unit increases the revenue by $1. Because we have the coefficient of d1 as 1, and by increasing the operation time 2 by single unit increases the revenue or profit by $2, because we have a coefficient of 2 over here. So this is the sensitivity analysis in algebraic form for the right hand side. And the third one, as it is 0 over here, it means that no change is in the optimal solution. No change in the z if we increase or decrease the time of operation 3 by a single minute, no matter how many minutes. The z will not change. We can say that z will not change by increasing time of operation 3. Now, for example, let's change the time of operation 2 by 25 minutes. Implies that 3x1 plus 0x2 plus 2x3 is less than or equal to 485. What will happen? Now you tell me, please.
We'll let you know in next lecture because the time is up now. It's almost 40 minutes.
Yes. But you can just give me an idea of it, like what will happen if we
increase
the time of the second operation by 25 minutes.
It's gonna increase.
Yes, it will increase definitely. But how much?
By
you send some problems on WhatsApp?
No, this was the big M method that I just told you about.
Okay. I will see it, and I will come with the solution for it. Don't worry.
It's okay if you add more light to it.
Okay. So you see that we have been doing
Or it's fine, it's fine.
Yes, I will.
Okay.
Now it's better?
Yeah.
Okay. So we had this problem of maximization, and it had like three variables. And in the algebraic method of it, what we did was that the first part is to change the right hand sides of the constraints. So we change each of it by a variable d, and this variable is equal to d1 for the constraint 1, it is equal to d2 for the constraint 2, and d3 for the constraint 3. And di is actually the change in the right hand side of the constraint I. So I can be equal to 1, 2, or 3, like constraint 1, 2, or 3. So we have three constraints over here. So we will have like d1, d2, and d3. So we will change the constraint from this form to this form. We will get over here is x1 plus 2x2 plus x3 less than or equal to 430 plus d1. So d1 actually is the change that we do, that we increase the time from 430 to some value that d1 will give us. Similarly, the right hand side of the constraint 2 is changed by d2, and the constraint 3 is changed by d3. So here, if you remember, we equated the S1, S2, and S3 to D1, D2, and D3 row. So we don't have to, solve completely for D1, D2, and D3. So whatever in the final iteration we get the column for S1, S2, and S3, it will be the same for D1, D2, and D3. So when we put the data in the Torah, we actually found that this is the final tableau. So for the S1 column, we got in the 0, we got 1. So it will be 1 for D1, 2. For S1, in the second row, for X2, we got 0.5. So in D1 here, it will also be replicated as 0.5. Similarly, copying these three columns over here. Now, the objective value will be equal to 1350 plus D1 plus 2D2 plus 0D3. Just like we write over here. Okay. So now the value for x2 is this, and x3 is this, and s3 is the variable, the non-basic variable that we, the slack variable actually, because x1 here is equal to 0 as it is not available in this table. We have here z, which is the objective value, x2, which is the number of trucks actually, and x3, which is the number of cars, toy cars actually, and we don't have x1 over here, so x1 will be 0. Now what this thing represents actually, that z is equal to 1350 plus 1d1 plus 2d2, it means that changing the right hand side or the resources for operation 1 will increase the total z value by 1, and if we increase the resources used by operation 2 at the time for operation 2 by a single unit, the z value will increase by 2. Here I have also written it in descriptive form. Changing the time of operation 1 by 1 minute increases the revenue or z value by $1. So if we increase 430 to 431, let's suppose, the z value that we get is 1351. Okay, and if we increase the time of the second operation from 460 to 461, the z value, the new z value that we get is 1350 plus 2, because here in coefficient we have 2, so we will get $1352, and it is 0d3. It means that whatever the value is over here, like 421, 22, 23, 24, whatever, it is not going to change the value of z. So z will remain changeless if we increase or decrease the value of the third operation time. I have written it in descriptive form. Z will not change by increasing the time of operation 3 or decreasing it. It goes on both sides, increasing and decreasing. Now, we did some other calculations too. I guess we were here and we are going to continue this part of it. So, now we need to find the feasibility range for each of the feasibility range for each of the constraint. So we know that in the first constraint it says that let's change the time of operation 2 by 25 minutes. So what we get is 3x1 plus 0 to plus 3 is equal to 485. Now, what we say in this form, like z is equal to 1350, we have this new equation, and 1d1 plus 2d2 plus 0d3. Now, it says what will happen if the operation 2 time is increased by 25 minutes. So we know that by increasing the operation 2 time by a single minute, the new value is going to be 1350 plus 2. So the total change we get is, now we need to find the value of d2. d2 is equal to 25 minutes. So 1350 plus d1, we are going to ignore it because we are not changing the value of operation 1, or d1 over here is equal to 0, and d3 is also is equal to 0, and d2 is equal to 25. So here 2 into 25. So z is equal to, the new z is equal to 1350 plus 50, and it will give us $1,400. So the new optimal solution will be $1,400. You understand how I get it?
Yes.
Do you hear me?
Yes, I can. You just change the x1, the d2, then you change the values, then you equate it again.
Like here, in the second operation, total time is equal to 460. But it says that what if the operation time is increased by 25 minutes? So 460 plus 25 is equal to 485 minutes. So d2 is equal to 25 minutes. Now we are going to put the value of d2 into this equation.
Okay.
So z is equal to 1350 plus 2 into d2. d2 is equal to 25. So d1 is equal to d3 is equal to 0. It means that the resources are the right hand side of operation 1 and operation 3. These remains unchanged. Only operation 2 is changed. So the total change in objective value we get is $50, and we get the new objective value as $1,400. From 1,350 it will jump to $1,400, because for each unit change in the second operation, the objective value will be increased by $2. And for each unit change in operation 1, the Z value will increase by $1, because we have one coefficient over here. So it depends upon the coefficient of this equation, or the value of D1, D2 and D3 in the Z row. The value of D1 is 1 in the Z row, so it means that by increasing the time of resource 1 by 1 minute, it is going to increase the profit by $1. But if we increase the time of operation 2 by single minute, it will increase the Z value by $2. And if we increase the value of D3 by 1 unit, it is not going to change the Z value, because D3 over here in Z row is 0. Now you understand?
Yes.
Okay. Now we will go towards the feasibility range of it. The main point in this thing is that when we change the right hand side of the resources or the constraints, it is going to to change the feasibility. It is going to affect the feasibility of the model. But if we change the objective coefficients, the coefficients of the objective function, then it is going to actually change the optimality of the objective function or the model. So these two are because it will change the optimality. I will write it over here for you to understand. If we change right hand side RHS of constants, it is change feasibility. But if we are going to change coefficient of objective function, it is affecting or changing optimality of it. So this is the basic difference. Now we will find the conditions for feasibility, or we will find the feasibility range of it. Now, what in an equation we have for the basic variables? We have three basic variables over here. First one is x2, x3 and s3. So for x2 in the d context, we have x2 is equal to 100 plus 0.5 d1 minus 0.25 d2. So we will write it over here. Here we have x2 is equal to 100 plus 1 over 2 d1 minus 1 over 4 d2. For x3 we have 230 plus 0.5 into d2, or 1 over 2 d2. So we will write it over here 230 plus 1 over 2 d2. And for s3 we have 20 minus 2d1 plus 1d2 plus 1d3. So we will write it over here as 20 minus 2d1 plus d2 plus d3. Now, how we got it actually? We got it from the final W of it. This is how we got it. This is Z. For Z we have 1350 plus 1d1 plus 2d2 plus 0d3. For x2 we have 100 plus 0.5 d1 minus 0.25 d2 and 0 d3. For x3 we have 230 plus 0 d1 plus 0.5 d2 plus 0 d3. And for s3 we have 20 minus 2d1 plus d2 plus d3. So we wrote same equation over here for the feasibility range. Now for the feasibility, all of these must be greater than or equal to 0. This is the condition for the feasibility, that all the three basic variables, these must be greater than or equal to 0. Now we will put some values of it and we will check whether it is going to give us a feasible solution or it will go into infeasibility, because we said that if we change the right hand side of constraint, it is going to change the feasibility. So here we will prove it that it affects the feasibility of it. Now we have some values that we will change the right hand side with, and then we will see that if these three yield the value greater than or equal to 0, or any of them is giving us a negative value. So let's suppose we have the new operation time that available, for example, available operations time, new available operation times are such as for operation 1, operation 2 and operation 3. The new time here is 480 minutes. The second one is 440 minutes. Before we had 430 for the first one, 460 for the second one, and 420 for the third one. Now we have 480 for the first one, 440 for the second one, and 400 minutes for the third one. It means that we are increasing the time of operation 1 but decreasing the time of operation 2 and operation 3. Now we will find the value of d1, d2 and d3 over here, and then we will put those values in this, and we will find out which one is giving us a negative value. If any of it is negative, then we are going to say that this gives us, the solution is going to be infeasible. So the d1 actually is equal to, the first was
Anwar,
430 and it was changed from 430 to 480, so the total change is equal to 50 minutes. The d2 is equal to,
or zoom because I can't see.
now you can see it. Can
you zoom a little bit more?
Now you see?
Yes, now it's look good.
Just a minute.
It's okay if you can turn off the phone camera, the phone.
Okay.
Sorry,
so here,
the phone light. The phone flash. Because it's causing heat also. Yeah, that's good. Yeah, that's good.
Okay, I will, make the direction, my direction, like where I can, because it's night over here, so. So now you can see it.
Yeah, I can see. If you can just zoom a little bit more.
I will zoom it.
Yes, I can see. Yes, clear now.
Okay. For D1, we have 480 minus 430 because previously we had 430 minutes, but now it, yes, it is changed to 480. So we are getting a positive 50 value for D1 in the first case. In the second case, the D2 will be going to be actually negative because at first we had 460 minutes for this, but it has changed from 460 to 440. So we will actually find out 440 minus 460, which is give us minus 20. So it is giving us a value of minus 20. Now for the third one, we also have a decrement. It's not an increment because previously we had 420 minutes, but now we have 400 minutes. So the D3 will also be equal to 400 minus 420, which
I
will
can
give
see.
us
Can you zoom?
minus. Yes, I will. Can you see it now?
Yeah, try to turn off the turn off the light. Okay. Okay, now good. يا الله، ليش ما عندك أجهزة حديثة؟ يعني ليش ما عندك جهاز حديث تسوي
Okay.
فيه؟
So
شكيت
now
طيز.
we will put these value of D1, D2, and D3 in the above three questions, and we will see which one is coming positive, which one is following the condition, and which one is contradicting it. So let's put the values in the above equation. So x1 is equal to 100 plus 1 over 2, and D1 is equal to 50. We will put this value over here.
Same problem. Can you zoom?
And the other part of equation is minus 1 over 4. Actually, light is a bit, it will come in like 5 minutes. So, for that time, we have to be a little bit, we have to bear with it.
Because it's not look very
It's
clear.
like it's coming in 4 minutes. So up till then we have to, bear with it.
I can't see. This is the problem.
I will. Can you see it now?
No.
Can you see it now?
Better.
The light
Yes.
rod.
Yes, better now.
Okay, so we will now put the value of the D2 over here. So it will become 1 over 4 into d2 is minus 20. So the equation will be like this. So it will give us 100 plus 25 plus 5.
Or 10, because it's 20. I have to have 20 is 10.
Yes, it is equal to 100 plus 25 minus minus 5. So it will give us 100 plus 30 is equal to 130. So 130 is greater than or equal to. So x1 is satisfying the condition. Now let's us see, sorry, x2. It's not x1, it is x2. Now we will see for x3 that what x3. So x3 is equal to 230 plus 1 over 2 into d2 is equal to minus 20, which is equal to 230 minus 10 is equal to 220, which is also greater than or equal to 0. So it is also satisfying the condition. Now for the S3, we have 20 minus 2 into d1. d1 over here is 50. Okay. Now plus d2 is minus 20 and d3 is also minus 20. Now solving this thing, it will give us 20 minus 100, 20 minus 100 minus 20 minus 20. So it will give us this 20 and this 20 will get cancelled, and minus 100 and minus 20 is equal to minus 120, which is less than 0. So S3 is not satisfying the condition. So S3 is not satisfying condition. So if any of these three equations is not satisfying this greater than or equal to 0 condition, it means that it has gone to infeasible ranges. So here these changes are infeasible. These are not feasible changes. These are infeasible changes. Okay. So now we will move towards the next problem, which is the changes in the objective coefficients. And we can also find the feasibility ranges, but for feasibility ranges you have to fix one and change only one and fix the other two, or fix one and changing the other two. So in that we can find out the feasibility for any of the d1, d2 or d3, which says that like how much change that we can bring in d1 or d2 or d3. So the answer is, or the model is feasible. Now for the feasibility range, feasibility range, for
I can't fucking see anything.
D1. It means that we make changes only in D1, while D2 is equal to D3 is equal to 0. In the first resource, we make changes, but in the other two, both of them will remain 0. So we will use the same three equations that we used over here, these ones, and we will find out which one is, what is the feasibility for D1. So we know that x2 is equal to 100 plus 1 over 2 into D1 minus 1 over 4 D2. X3 is equal to 230 plus 1 over 2 into D2, and S3 is equal to 20 minus 2D1 plus D2 plus D3. Now we know that D2 is equal to D3 is equal to 0. So we will put these values over here. Putting values of D2 is equal to D3 is equal to 0 in above equations. Now in the first equation, what we get actually? We get x2 is equal to 100 plus 1 over 2 d1, because there is no d2 over here. D2 is equal to 0, so minus 4, I should write it into 0. So it will give us 100 plus 1 over 2 d1, which implies that d1 is greater than or equal to minus 200. This 100 will come to the other side of the equation, and this 2 is denominator, so it will multiply with the 100, so it will make minus 200. So it means that the minimum range for d1 must be minus 200. So minus 200 is the change that we can make in the d1, the minimum. We can make it up to minus 200. Now what will be the maximum? For the maximum, we must explore the other two equations. So x3 is equal to 230 plus 1 over 2 d2, implies that d2 is equal to 0. So this is kind of useless for us. Now doing it for the third one, we get 20 minus 2d1 plus d2 plus d3. Now we know that d2 is equal to d3 and it's both of them are equal to 0. So we get s3 is equal to 20 minus 2d1. So we want to find it for the d1. So we will change, or we will transfer 2d1 over here. So it will become positive. So d1, it must be greater than or equal to 20 by 2, which is equal to 10. So the feasibility range for the d1 is minus 200 less than or equal to d1, and it must be less than or equal to 10. So this is the feasibility range. If we make the changes in resources, less than or equal to 10 and greater than or equal to minus 200, the answer or the model will remain feasible. Now from this, if we make actually this equation over here, where is the constraint? This one. If we make 430 is equal to 441